Hello, students. Last time we talked about the beginnings of statistics and what that means. And basically, what we talked about was after we collect data and we have this good data that we've collected, we try to summarize it in some way visually. So we looked at several kinds of graphs. We looked at bar charts, we looked at pie charts, we looked at histograms, we looked at stem and leaf plots. And so those are good summaries of distributions, but in many ways there are, how should I say, there are many ways to talk about distributions and not just simply looking at the shape of some graph or something like that, but we can be more specific. So, two particular numerical descriptions of distributions are ones that involve a measure of center of that distribution. And so you can kind of think of a measure of center as average, but we're going to look at other measures of center other than averages, and the amount of variation around that average. So how much variation is there within a data set? So that's what we're going to talk about today. And yes, we have a lot on our plate today, so we'll get going. So here it is. What are some common statistics that you hear about on the news, radio, maybe advertisements, something along those lines? And generally, I think we hear a lot of averages. We hear a lot about averages. We hear a lot of percentages as well. For example, 68% of the people that we polled would vote for candidate A in November, or something like that. But it also might be something along the lines of the average household has 2.5 cars in their garage. Now, that might sound a little bit strange, but the idea with something like that is that it's somewhere between 2 and 3, generally speaking. So, but we'll talk a little bit more about that and as we go, and hopefully when we get into some more examples, it'll make a little bit more sense. But one thing I'd like to warn you about first, before we begin any of this, is that averages can be sometimes misleading, and we're actually going to talk a little bit about that. But the first one that we're going to talk about, the first measure of center, is this arithmetic mean, or average as we know it. Probably from grade school. I remember looking at averages when I was in, 6th, 7th, 8th grade, something like that, and I forget. But there it is. So it's one measure of center, and we're going to be looking at others. And like I said, averages can be, how should I say? People like to use averages in clever ways that are maybe a little bit misleading sometimes, and we'll talk about how that can happen today. So there it is. And actually, there are several ways that we can abuse averages, but we'll talk about those as we go. All right, but that's not to say that averages are bad. When they're used well, when they're used for the purposes of good and not evil, then averages can be a really nice thing. They can be a really handy description of a distribution. So let's get down to the business of computing some averages. So again, it's that idea. Hopefully you are already familiar with what an average is. And if you're not, then, we got you covered. We can still take an average here. So basically, the average of this collection of 5 numbers is you add them all up and you divide by the total number. You divide by 5. So we get an average of 4.4. So suppose that, you do some kind of survey or something like that, and this is the number of cars that somebody has owned in their lifetime, and this is a random sample of people that you, on campus or something like that. Then the average of your sample is 4.4 cars over their lifetime. So what that means is that, they don't own, you can't own 0.4 of a car, but what it does mean is that usually it's more around 4, but sometimes it's around 5, but it can stray even further from that sometimes, as we've seen in our data set. But this is some middle value. This is a value that sort of gives us a characterization of the middle. So, if you like fancy mathematical notation, well, here it is for you. If you want to represent x bar, that's another name for this average, this arithmetic mean. So to find the arithmetic mean of n data points, you add up all of those n data points, and if you like sigma notation, you can use sigma notation as well. You add up those n points, you divide by the total number of points n, and you have your arithmetic mean. So there's a nice formalization of an average. Okay. So very often what will happen is that we will be given grouped data. So when data is reported, very often we have many values that are the same. So for example, we have, this is actually a real data set. So what we have is the number of servings of fruit claimed by 74 17-year-old girls. In other words, it's the number of servings that they claim to eat each day. So, and this was actually a real study in Pennsylvania. So how can we calculate the mean for this group data, right? So one way we can do that is to just say, okay, well, right, we add 15, or we add 0 to itself 15 times, so 0 plus 0 plus 0 plus 0, 15 times, plus 1 plus 1 plus 1 plus 1 plus blah, 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 11 times, plus 2 plus 2 plus 2, 15 times, so on and so forth. But we don't want to do that. That's why we invented multiplication. So what we can do is we can just say 0 times 15, right? To get the total servings of fruit, we can just do 0 times 15 plus 1 times 11 plus 2 times 15 plus 3 times 11, and that'll give us the total number of servings of fruit that these girls ate. So there it is, 0 times 15 plus, if we go, so 0 times 15 plus 1 times 11 plus 2 times 15 plus 3 times 11, so on and so forth. Right? We add all those up, and what we see is a total of 194 servings a day eaten by these 74 girls, right? We just added up this column, right? The frequencies. So the frequency is just the number of times that something occurred. It's the number of times you observed that value in your data set. So again, right, we observed 2 servings of fruit for 15 girls, right? So 2 was written down 15 times in our data set. All right. Now, I gave you earlier that we had 74, but that number may or may not be given to you. So if you need to know the number of people in your sample, you can just add up the frequency column. And in this case, the frequency column is on the right. All right, so to find the average, you basically just take the total number of servings, divide by the total number of girls, so you have servings per girl, and hey, there it is. That's 2.62. So the average for this sample of girls, the average reported number of servings of fruit per day for these girls is 2.62. So that is sort of a middle value. That's a measure of a typical value for this particular data set. Okay. So we could have done this as well. So let's go back to the idea of a histogram. Remember that a histogram is just a visual representation of this frequency table. That's really all a histogram is a visualization of this data. So we could have done these calculations from the histogram. In other words, we could have said, okay, well, we know that, right, we have 15 girls who ate 0 servings of fruit, plus, what is that, 11 girls who ate 1 serving of fruit, so 11 times 1, plus 15 times 2, plus 11 times 3 plus, what is that number, 8 times 4, so on and so forth. So you could actually get it from the histogram as well. So that's a pretty nice thing. So, and again, that's another reason why graphs are so useful as well, because they not only give you a sense of how something like, for example, servings of fruit is distributed, but you can also calculate a group mean from it as well. So either from a frequency table or a graph. Okay. Now, sometimes we are given continuous data, and we've looked at examples of continuous data before. So what we have is a frequency table for a random sample of mileages for 30 cars. And what we're going to do is estimate the mean from this group. Now, we can't compute the mean exactly, because very often what happens with a frequency table like this is they just give you sort of mileage categories. So, like, for example, they just give you categories or intervals in which their data set fell. So, for example, we have 4 cars in our data set that got between 15 and 20 miles per gallon. We have 3 cars that got between 20 and 25. We have 6 cars that got between 25 and 30. So on and so forth. But the idea here is that, okay, well, we don't know what the individual values are, but if we were to take the average of whatever the values are in this interval, it would probably be close to the middle point of these values. So, for example, if I took, let's go ahead and try, so for example, with 7 data points, if I took 7 data points here, and I were to add them up, I would probably get something that is close to the 35 plus 40, right, which is 75. You divide that by 2, right, you get 37.5. So the midpoint here is 37.5. So we expect the average of those 7 values, well, to be approximately close to that value. Now, it's probably not exactly equal, but it's close. It's an estimate. So that's how we are going, based upon that assumption, that is how we are going to estimate the mean. Okay. So what we're going to do then is say, all right, well, to estimate the total mileage driven by these 30 cars, we're going to take the midpoint of this interval times 4. Midpoint of this interval times 3. Midpoint of this interval times 6. In other words, right, so on and so forth. In other words, what I'm going to do is say 17.5 times 4 plus 22.5 times 3 plus 27.5 times 6, so on and so forth. That will give me the approximate number of miles. So you can see again here that I have midpoint. Let me see if I can get that up here. Yeah. So midpoint times frequency, midpoint times frequency, midpoint times frequency, and so on and so forth for all the values. So we get a total of 935 miles approximately driven. And we have a total of 30 cars. Now, again, I gave that value to you up here, but you may not always get this value. In other words, you may have to add up the frequencies. In other words, the number of times each data point was observed. And so we get the number of cars, which, oh, here, hold on a second. Let me do something here that's a little bit strange. Okay, and we're back, and I fixed that little mistake there. So there it is. So in other words, all I do is I add up the frequencies of the vehicles, or how should I say, the frequencies of not vehicles but mileages. So again, 4 vehicles had the first mileage category, 3 vehicles had the second mileage category, so on and so forth. And there we have it. So we have a total of 30 cars. So the number of miles per car on average is 31, or how should I say, miles per gallon, right? Let me see, let me just make sure. Yes, miles per gallon ratings. So in other words, the total miles per gallon, right, divided by 30, and what we get is an average efficiency of 31.17 miles per gallon. So you can actually get that from the table as well. So again, that's just an estimation. This probably isn't the exact value, but it's probably pretty darn close. So there you have it. All right, so you can do the same thing here. Now, here's a histogram of the values, right? You can see we have the same frequencies that we had before. We had 4, 3, 6, 6, 7, 3 and 1, which are the same frequencies we have in the right-hand column there. And we saw that, again, there were 4 cars for which their mileage was between 15 and 20 miles per gallon. There were 3 cars for which there were between 20 and 25 miles per gallon. There were 6 cars for which they got 25 and 30 miles to the gallon, and so on and so forth. But you can get that from the histogram as well. And you can almost even eyeball it. If you look at the center of this distribution, and you can see it's roughly symmetric, so I'm throwing around a little bit of vocabulary here. You can see, right, 31's about here. You can see that that's about the center of the distribution. Similarly, if we go back up to the to this example, 2.62, we can see that 2.62, somewhere in there, this is actually a kind of center of the distribution, and it's probably pulled up a little bit because this kind of distribution is a bit skewed to the right, as you can see, and it pulls that average up, and we'll talk more about that as we look at some other examples. So that's one way that you can you can pull shenanigans with averages, is when you're dealing with skewed distributions like this one, for example. We'll talk more about that as we go. Okay, so here's another measure of center, and that is the median. Now, if you're wondering, okay, I have a mean, I have a median, how am I going to keep track of both of them? I remember my stats teacher telling us that, I remember my stats teacher asking us, when I took stats for the first time, she asked us, well, do you know what that thing in the middle of the highway is called? And a few people said, well, it's called the median. She said, well, it's called the median because it's right in the middle of the highway. And from then on, I always remembered the term median. So yeah, if you think about that thing that's in the middle of the highway that divides it right down the middle, that is the median. And basically that is what this measure of center is. It's the one that's right in the middle. So, for example, if I wanted to find the median of this data set, one thing you'll notice is that it is in ascending order. So when you actually find the median, you have to arrange your data in ascending order. And that one in the very middle, right? So you can see for this first data set here, that one in the very middle is the median, right? Because it's in the middle of the data set. Now you might be wondering, well, what if we have an even number of values? Well, there's an answer for that, and that is take the average of the middle 2 values. So you can see that these 2 values are physically in the middle. You just take the average of them. So the median of this highlighted set would be 4.5. So that's basically how we take a median. You just look at you arrange your data set from smallest to largest, and you look at the value that's smack dab in the middle, and you will have your median. All right, so let's look at this value right here, or this stem plot here. So basically, it's kind of like a sideways histogram, as we saw. We did a little bit with this last time. And what we have is, this is actually a random sample of 15 workers in North Carolina. And these are travel times to work. And you can see just from the stem and leaf plot here that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 values. And basically you can see from here that it is essentially, you can see that they're arranged from smallest to largest. Now, if I wanted to take the mean of this data set, well, we just simply have to translate that into actual numbers. So again, this will be like a little, whoops, okay. This will be a review of stem and leaf plots. So here the stem is 0, but the idea is that 0, 5 is just 5. Plus 10, and I'm going to do 10 times 4 because there are 4 values of 10 here. So I'll do 10 times 4 plus 12, right? So 1, 2 is 12. 1, 5 is 15 plus 20 plus 20. So I did that twice, plus 25 plus 30 plus 30 plus 40 plus 40 plus 60. Great. And there we have it. So we have a total of 337 minutes, and that is divided by, so I'm going to take that whole value here. I'm going to divide that by the 15 workers, and whoops, that gives me an average commute time of 22.47 minutes approximately. So there's the average, if you like. Now here is the median. So the median is the value that's right in the middle. Now here's a fun sort of thing that you can do, and this is a nice formula, if you will, for the median. So if you take a value like, let's see, we have 15 data points. If I add 1 to it and I divide by 2, that will actually give me the median. So in other words, if I take 15 plus 1, that equals 16 divided by 2, we get 8. And so that gives us that middle value. So in other words, when we take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, that 8 gives me, well, let's see, if we go 1, 2, 3, 4, 5, 6, 7, 8, right there it is, 1, 2, 3, 4, 5, 6, 7, 8. Here's the 8th, well, okay, here's the 8th value. And you'll see that there are 7 values below it. All right, now if we look at above this 8th value, there's 1, 2, 3, 4, 5, 6, 7 values above it. So that is the median. In other words, there's 7 values below it, 7 values above it. How did I find that? Well, I took the number of data points. So if you like, I can say n in general, n plus 1 over 2. And basically what you do is you round down to the nearest integer. So you take the floor of that value. So in other words, what I would do is, and maybe we'll go into an example in just a second, but for example, if I said, okay, the floor of n plus 1 equals 2, or pardon me, n plus 1 over 2, right? If I did that for a different data set, I would get something different. So in other words, this will tell you the location of the median. So maybe we could say the location of the median in that ascending list is given as is given by this formula. So for example, if I had 15 data values, right, the median would be the 8th data value. So for example, suppose I went back and I wanted the median of this data set here. we'll notice that it's going to be in between here. And actually, I guess I could just say, I could skip the floor part, and I could say this. I could just say, all right, well, I have 4 data points plus 1. And so we're going to suppose here that n equals 4, right, from that other data set, divided by 2. That equals, what, 5 divided by 2 equals 2.5. In other words, it's the value between, so actually we don't need any of that floor stuff. It's the value between the second and the third data point. So in other words, in this case, 4.5, right? So that's, so the median in this case would be 4.5. All right, but the idea here is, right, and actually you don't even need the floor in this case. Perhaps I was getting a little bit too ahead of myself there. But the idea is that finding the median is not a difficult thing to do. There's even a formula for which location it's in. So 2.5 means that it's in between 2 and 3. The values 2 and 3. You take the average of the second and the third value. That's what the 2.5 means. Okay, so so the median then is 20. So we saw that the average is 24 or 22.47. There's the average, and the median is 20. So you can see that they're close to one another. But one of the things that I would draw your attention to is this idea that there's kind of a longer tail out here. It's a distribution that's skewed to the right. And because of that, it pulls the average up a bit. And so that's something to think about. That's something I'd like you to think about as we proceed further here. So yeah, and this next example gets at that idea right now. So if I were to ask you, what is the median of this data set? Well, I'm hoping that you'll be able to say, okay, there are 1, 2, 3, 4, 5 values, and if you take n plus 1, you divide by 2, that's 5 plus 1 divided by 2 equals 6 over 2 equals 3. So it's the third value. So we'll look at 1, 2, 3, right? There's the third value. That's the one in the middle. So in other words, this formula here gives you the one in the middle. All right, so the middle value, the median value, is 4. But if we were to take an average of these, let's do that. I'm going to clear this out. What you'll see is, well, something that is quite a bit different. So I'll add 3 plus 3 plus 4 plus 5 plus 1 million. All right, and when I do that, I'm going to add that. That's the sum of those numbers, and when I divide by the 5 values that there are, we get 200,003. So as you can see, what happened here is this outlier really influenced that mean. So in other words, the median stayed steady here. In other words, the median didn't move when this upper value is extreme. So on the other hand, the mean was pulled toward that value very much so. In other words, the mean is easily influenced by outliers and extreme values. So, so this is an important thing to know about averages, because this is one of the ways that averages can be abused, and we'll talk about that right now. So let's suppose that you have a realtor who is maybe not quite on the up and up. They're a bit shady, and hence their name, Shady Real Estate. And they're advertising a property somewhere on Klickitat Street. And we're just going to suppose that this is a bad area of town. But For whatever reason, and yes, it's very strange, we have an eccentric billionaire who has decided to build a house on this street. So maybe they want to get in on, sort of on the ground level in gentrifying the neighborhood or something. Who knows what is going on here? Who knows what goes through eccentric billionaires' minds? But here it is. These are the following prices, right? So we have, like I said, this is a really bad area of town. So the houses are falling down, and I don't know, lots of bad stuff. So, for example, the first property is $10,000. The second property is $20,000. The third property is $35,000. So on and so forth. But this last one is a $10 million home. So again, this billionaire, for whatever reason, decided to build their $10 million mansion, or one of their $10 million mansions on Klickitat Street. So the question I would ask you is this. What do you think, if they're really shady, if they're dishonest in how they report a middle value, what value, if they're shady, do you think they're going to report? So I would say, well, let's take a look at both of these. Let's take a look at the median, and I think you can see that the median is going to be the average of these middle two values. So let's look at what the median is first. So the median, if we take 35,000 plus 42,000, and we divide by 2, we get that this is the median property value, 38,500, right? Now, any realtor that is honest and worth their salt is going to give you a median value. Because you go to any town, you move to any area or any town, and there's probably going to be some skew because, man, there are some nice houses. For example, here in Coos Bay, there are some really nice houses up on the hill, and I imagine they're probably, worth something, and they probably might pull that mean up a little bit, just like this one is about to do. If we take the $10,000 property, so I'm going to take all of these, and now I'm going to find the average. So again, what I'm going to do is write this down as the median. In this case, is 38,500. Let me just make sure I have that correct here. Okay, 38,500. Boom, there it is. Now we're going to calculate the mean, and we're going to see what happens here. So if we do there it is. Good. All right. So if I take that 10,000 plus 20,000 plus 35,000 plus 42,000 plus 60,000 plus 10 million, 123, and I'm going to divide that by 6 properties. Well, hey, look at that. Let's see, 1,694,500. All right, so let's plug that in there. So there it is. So here's the median, so 38,500, and here's the mean, 1,694,500. All right. So if you are a realtor, if you're a shady realtor, probably what you're going to do is tell your clients you'll report the mean. But any realtor, and actually, I don't know what the laws about regarding realty and all that stuff are, but I imagine they need to report the median, because the median, as you can tell, I think is more reflective of a typical price. It's a better measure of center in this case, because typically these real estate values tend to be skewed to the right, because you do have those few properties in town which are worth a lot of money. But most happen to be clustered around some middle value, some median value. And that's why any self-respecting realtor is going to give you the median and not the mean. So if you're ever in doubt about that, make sure that you are getting a median and not a mean. Okay, so again, anytime there's skew in a distribution, either skew to the left or skew to the right, just like we've seen here, we've seen some extreme skew to the right because of this $10 million property value. That is when it's time to ask for a median and not a mean. Okay, so there's a savvy citizen fact here, and that is that the mean is very sensitive to extreme observations and outliers. So, on the other hand, the median is pretty steady. It's not affected by large values all that much. It takes a lot of larger values to raise that median up. So, in other words, you have to change the entire distribution to make that sort of thing happen. So this is one reason why the median is called a resistant measure of center, because it is resistant to extreme observations. The mean is not. The mean goes wherever the wind blows it. So if there is an extreme value somewhere in a distribution, the mean is very starstruck. It gravitates toward that larger than life value. And so it's pulled in whatever direction any large value in your data set resides. So the mean is not a resistant measure. So that's something to keep in mind whenever somebody presents summaries of data for you. Okay, so here's the thing is if a distribution is symmetric, then the mean and the median are going to be pretty close to one another. If you have sort of a mirror-shaped symmetric sort of distribution, or at least roughly symmetric. On the other hand, if you have extreme skew to either the right or the left, the mean is usually farther out, closer to those long tails. So, for example, if we go back to this example here, the commute times, we saw that the median was 20, but the mean was 22.47, I believe, if I'm not mistaken. In other words, was pulled out a little bit by this tail. So this is a skewed to the right distribution here. It was pulled out just a little bit by that tail. So that's something to think about. And this is a general property of means and medians and modes as well. So we haven't talked about the mode yet, but I will talk about the mode in just a second here. So anytime you have something which is skewed to the left, the mean is going to be the furthest one out. In other words, it's pulled toward that tail. It gravitates toward those extreme values. So this green bar for this left skewed distribution, this one would represent the mean. The middle one would represent the median, and the hump here, the most common value in a distribution is actually called the mode. So in this case, the peak of that distribution would be the mode. Here, the mean, the median, and the mode are the same thing. Here, on the other hand, the mode again is where the peak occurs. The median here is where the right is the one in the middle, but again the average, the mean, the arithmetic mean, is the one that is gravitating out toward the tail here. So it gravitates toward those extreme values. So that's a good thing to know about averages, right? Also, things to know between means and medians. And the mode, and I should say, just to clarify here, the mode occurs in the mode is the data value which occurs most frequently. So for example, in this data set, 10 occurred 4 times, so 10 would be the mode of this data set. Here, 3 would be the mode of this data set because it's the one that occurs most often. Here the mode is all 4 values, right? The mode is not necessarily unique. Here the mode is somewhere between 35 and 40 miles per the gallon. And here we actually have two modes here. This is actually kind of what they'd call a bimodal distribution because there's two peaks. So the two modes are 0 and 2 in this case. So those represent the most frequent values. So that's something to think about. It's not something that I'm going to emphasize a whole lot, but I at least want you to know the most common measures of center, and that is mean, median, and mode. The emphasis will be on means and medians. Okay. Now, here's the thing, is that measures of center are not enough of a summary to give you a good sense of a distribution. So, what should I give you? Well, number one, I should give you a graph of a distribution. I should give you some measure of center, but I should also give you something else. This is another important thing, and let's talk about what that should be. So if I gave you these two data sets, you will see -1, 0, and 1. Okay, so that's data set 1. Data set 2, I have -1,000,000, 0, and 1,000,000. Now, hopefully you'll notice is that at the mean and the median of both of these distributions are 0. They're all 0. So, but I think you can see that both of these data sets are fundamentally different. In other words, this one, this -1,000,000, 0, 1,000,000, is way more spread out than this one. So, in other words, what we're getting at here is that we need some other figure that tells us how spread out our data is. In other words, how much variation there is between data points. And let's get at that right now. So suppose, so here's another example for you of why we need to know a measure of variation, and that is Sleazy P. Martini is a real estate agent for Shady Real Estate. So you remember Shady Real Estate, and perhaps you remember Sleazy P. Martini, depending on what topics we've covered already. So he's trying to entice you to buy a property for which he says the average yearly temperature is a lovely 60.2 degrees. Sounds great. Sounds awesome. Where is this place? So, but you, as a statistically savvy citizen, you need to ask some questions first. And I would say the first question that you're going to ask is, well, how much variation is there in temperature? What are winters like? What are summers like? And if Mr. Martini, if Sleazy P is going to be honest with you, well, he'll give you the data set. And that is, well, what he's trying to sell you is a property in Oklahoma City. So the average yearly temperature, well, and this was way back when, so this may not be the case anymore. I'll have to look it up on Wikipedia. But back when this figure was drawn, and actually you can see that this figure was drawn some years ago, right? You can tell by the graphic design. But anyway, let's just say, okay, fine, it's 60.2 degrees. Look at how much variation there is between the highest and the lowest temperature. So the lowest temperature is 17 degrees below zero, and the highest is 113 in summer. So you can see that, well, in its most extreme, at the extremes, there's quite a bit of variation. But even if you look at average high temperatures and low temperatures, there's still quite a bit of variation, and that's something that you need to understand. And that is something, if somebody gives you an average and they don't tell you how much variation there is in something, then that is a red flag. That is a surefire, well, I don't want to say it's a surefire sign, and it might not even be that someone's trying to intentionally mislead you. It might be that that they really want to make a certain point. But the idea is, be suspicious. Anytime someone gives you an average or some measure of center without some measure of variation, Be wary. And one reason I would say that is because, well, here's a fun little quote. A person with their feet in the freezer and their head in the oven is on the average quite comfortable. So, right, you can take that one to the bank. And this gets to that, another savvy citizen fact, and that is any description of that is actually useful, that you can use, will not only give you a measure of center, but also a measure of variation. How much variability is there in a data set? This is an important piece of information that you should always ask for if someone is trying to sell you something. So let's do this. We will actually quantify this later, but if I were to go through these data sets and arrange them in order of the least amount of variation to the most amount of variation, this set here has no variation whatsoever. If you say 5, 5, 5, 5, 5, 5, well, there's no variation. From data point to data point, there's no change. There's no variation. Variation is 0. And we'll see that the measure of variation that we come up with a little bit later, or I should say several measures of variation, but there will be one particular number that we'll be looking at a little bit later. This one has more variation, but not the middle, or this set has, this highlighted set here has more variation than the 5 set here, but it certainly has less variation than this set. This highlighted set has a lot of variation, sort of thrashing around from 26 to negative 50 to 4 to negative 40 to 40 to 50, right? It's just moving around all over the place. Whereas this one is, right, the one that I'm highlighting right now, this second data set is, there's some variation, but it's not nearly as violent, if you will, as this last set. So we need to find ways of quantifying this variation. So, so the first thing that we're actually going to look at is how spread out data is. So travel times in New York State. So before we looked at North Carolina, now we're going to look at New York. So travel times in New York State are longer than in North Carolina. And here are 20 randomly chosen travel times, commute times for New York workers. And you can see that, right, it's sort of randomly chosen here. But what we're going to do is that same thing that we did before. We're going to arrange them in order. So we arrange the data set in ascending order, and you'll see that what I have here is I have a lower half, I have a lower 10 values, and I have an upper 10 values. So you can see that the median of this data set is 22.5. It's the middle point between these two values. And to get at variation, what we're going to do is divide this set up even more. We're going to look not only at this median value here, but we're also going to look at the medians of both this lower and this upper set. And that gives us these values right here. So in other words, the median here is going to be 15. We saw, or right, the median of this lower half of the data set is 15. The median of this upper half of this data set is 42.5. So basically what we've done by looking at the median of the entire data set plus the median of the lower half and the median of the upper half, what we've done is we've divided our data set into quarters. So we have the lower 25% of our data, we have the next 25% of our data, we have the another 25% of our data, and we have an upper 25% of our data. And we can summarize this distribution with 5 numbers, and they are that lowest value. So look at that lower value. You can see that this value here is the largest value. So you have this min, you have this max, And everything else, oh, and this should look familiar, this middle number is the median, and those values that divide the upper, or how should I say, in other words, that divide that lower half in two, that is this second number. And if we look at the upper half of our data set and we look at the median of that, that's this fourth number here. Now, each of these, this number here, well, let's start from left to right here. So this value of 5 gives this is the minimum value of the data set. This 15 is called the first quartile. This value is just simply the median of the data set. This value, in other words, that midpoint between these values here, is 42.5, and 85 is the maximum. And this is a really nice way to summarize the distribution. You can see how much variation there is. As a matter of fact, you can see that 25% of your data lies between these two values. 25% lies between these two values. The next 25% lies between these values. And the next 25% lies between these values. And what that tells you is not only how spread out the data is, because you can see the minimum value and the maximum value, but it also gives you the median. It gives you that measure of center as well. But it gives you a little bit more. It actually gives you a good sense of what the distribution is and if there's any skew or not. So for example, if we look at these, if we look at the min, the median, and the quartiles, you can see that if we compare this value of 85 to it, you can see that that appears to be a rather extreme value. And it is. And we'll talk about isolating extreme values in just a second. But anyway, there it is. So this set of numbers has a very particular name, and it's called the 5-number summary. So, and when we put these 5 numbers together, again, for any data set, when you report that minimum value, that first quartile, the median, the third quartile, and the maximum value, that gives you what is called the 5-number summary. And it is a standard way to report or to summarize a distribution. So it's a nice way, just simply a set of 5 numbers, you can give your reader a good sense of not only the center, but how much variation there is in your distribution with only 5 numbers. That's pretty nice. All right, and if we plot this data too, this is always a good thing to do. Plotting our data is a good thing. We can see that this is the data set that we just looked at, and you can see that the median falls between this 0 and this 5. In other words, right, it's that 22.5. So this is a different distribution than we saw for the North Carolina, but it looks similar. You can see that it's skewed to the right, just like the one for North Carolina workers. And here's a way to graphically display the 5-number summary. And this is another graphical technique which the 5-number summary gives us. So a box plot simply plots on a number line. In this case, it's a vertical number line. Sometimes it can be horizontal as well. But if we look at the minimum value, right, we put a little tick there. The first quartile of 15, we put a little tick there. There's a median, we put a little tick there. The third quartile, we put a tick there. And that maximum value, we put a tick there. Around the first and third quartiles, in other words, that middle 50% of your data fits inside the box. So in other words, you draw a box around that middle 50%. In other words, those 2 quartiles, those 2 middle quartiles. And what that gives you is a good sense of where the middle of your distribution is. The endpoints, how should I say, these little whiskers. Now sometimes this is actually called a box and whisker plot because of these little whiskers that come out here. But you can see that these endpoints give you a sense of the end behavior, if you will, of your distribution. Now, if you see a really long whisker, that might be an indication of an extreme value. So in this case, 85 seems like a bit of an extreme value, and you can actually see that better from the box plot than you can from just simply the 5-number summary. Now, you can pluck that from the 5-number summary, but again, the graphical summary says a lot. A picture is worth 1,000 words in statistics. It really is. So, and if we compare that to the distribution itself, you can sort of see that, okay, 50% of our data values lie somewhere in here, with some more extreme values up here, but not nearly as many, right? It's sort of, we can see that it's skewed to, well, I know it looks a little bit strange the way I've done this here, but it's skewed to the right. So, so there you have it. So there's a comparison between the box plot and the stem and leaf plot. All right. So here's a pop quiz for you. Do you remember what an outlier is? So think about it. Think to yourself if you remember what that means. You could pause the video and try to remember what that means. But basically, an outlier is just an extreme value. It's something that falls outside of the overall pattern. So we can see here in this commuter data, and in this case, I think it's it's the New York travel time data, that 85 seems to be an extreme value. Now, it may or may not be an outlier, but sometimes calling an outlier can be a judgment call. But there is a way to objectively say whether or not a point is an outlier, and that's what we're going to do right now is figure that out. So you kind of see the general pattern seems to be a distribution that is skewed to the right a bit. And so this value of 85, right, that's the one that gives that puts that bar in the histogram there. Is there an objective way to say that 85 is or isn't an outlier? And there is. And it's actually called the 1.5 IQR rule. Now, you don't know what IQR means, but I will show you what that means right now. So IQR means the interquartile range. So let me write that down here real quick. So this is the interquartile range. In other words, that is the IQR equals the interquartile range. And what that means is if you look at the interquartiles of your data, right, here they are. So you have, the quartiles again. Well, if you look at that middle 50% of your data, that middle 50% of your data falls between, well, again, remember, here's 25% falls between these values. 25% of your data falls between these values. So 50% falls between these values. So your interquartile range is the amount of variation or the spread between quartile 3 and quartile 1. So to get the interquartile range, all you have to do is subtract quartile 1 from quartile 3. In other words, quartile 3 minus quartile 1. That is what your IQR is. So what we're going to do is say, well, and if we look at this, right, so essentially the interquartile range is the length, or, right, I should say, this length here. It's the length of that box. in your box plot. So in this case, the interquartile range would be, well, what is quartile 3? It is 42.5. Minus 15. And when we put that into the calculator, 42.5 minus 15, boom, there it is. 27.5 is the interquartile range. So 27.5. So what that's saying is there's a spread of 27.5. In this case, we're talking about minutes, 27.5 minutes, in the middle 50% of our data set. All right, so that's what the interquartile range is. Now, when we want to identify if something is an outlier or not, if anything falls 1.5 times that interquartile range, so if we think of this length, if anything falls 1.5 above that, or 1.5 below that, right? Or in other words, I should say 1.5 of that value above, or 1.5 of that value below, then it would be considered an outlier. So in other words, if we looked at this length, this 27.5, and let's actually calculate, what is that? 1.5 times the IQR. That equals 1.5 times 27.5. So let's do that right now. 1.5 times 27.5, and we get 41.25 equals 41.25. All right, so in other words, if we look at any value that's 42.5, or wait, sorry, or 41.25 above 42.5. So again, 41.25 above 42.5, and anything below, what is it? 15 minus 42.5, or sorry, 41.25. Then we have an outlier on our hands. So let me show you how this is done. So, so does this data contain any outliers? That's what we're going to find out right now. So we're going to see if 5 or 85 or anything else in between qualifies as an outlier. So again, the whole idea is, fine, identify what your quartiles are. So quartile 3, 42.5. Quartile 1 is 15. Compute the interquartile range. So we did that. We get 27.5. And so when we do this, when we do quartile 1, right, and we look below by 1.5 of its interquartile range, that's this thing right here, anything that falls below negative 26.25 would be considered an outlier. So we don't have any values like that at all. As a matter of fact, all of our values are positive. So there are no outliers below here. So in other words, 5 or anything else wouldn't be considered a lower outlier. Let's look at the other one. Let's look at the other side of the coin here. So that's the lower. If we look at the upper, well, then we're talking about quartile 3, in other words, the top of the box, up to 1.5 times the interquartile range. So that would be this value right here. And so what we see is anything above 83.75 is considered an outlier. So do we have a data point which is greater than 83.75? Yes, we do. Turns out that 85 we saw that 85 is a part of our data set, and it is an outlier. So this is the only outlier of our data set. And the 1.5 IQR rule showed us that. In other words, that rule, and it's not the only rule, but it's the only rule we're going to study in this class. According to that rule, 85 is considered an outlier. So, and it's pretty common to identify outliers with that method, the 1.5 IQR rule. Okay, so there's an example for you. All right, so we're going to talk about another way to measure variation. So we've seen that looking at the 5-number summary and its box plot gives us some sense of the amount of variation. Looking at a histogram also gives us a sense of the amount of variation. A stem and leaf plot will do the same thing as well. But what we're going to do now is look at a way of encapsulating all of that variation. In other words, measuring the amount of total variation in a data set by a single number. And that number is called the standard deviation. So, and it turns out that this really is the most common measure of variation. So, other books sometimes call this measures of spread. Spread also has a technical meaning aside just being a synonym for variation. But we won't worry about that so much. But here, the most common measure is standard deviation. Basically, the way to think about standard deviation is like the average difference or the average distance a data point is from the mean, from the center of the distribution. Now, when I say distance, we have to be really careful because we're not talking about an absolute value. We're talking about something different here. So by average deviation, we will be a little bit clearer here in just a second. So, but I'm going to give you some values of the standard deviation just so you know that the idea of it really does make sense. So if I looked at this data set, you can see that 2, 2, 2, there's no variation between data points. So you would think the standard deviation should be 0, and it is. That number that we are going to invent in just a second here will be 0. In other words, there is 0 variation in this set. On the other hand, if you look at the average of this set, the average is 2, and the most typical deviation from that average is 1. And yes, it turns out that the standard deviation in this case is also, or I shouldn't say also, but the standard deviation is 1 in this case. Here we have an average of 2, and we see that the average deviation, if you will, from this mean is 2, right? The distance between 0 and 2 is 2. The distance between 2 and 4 is 2. And so, right, the sort of typical deviation of any point in the data set from the mean is 2. So, and it really turns out that the standard deviation really is that number. Now, standard deviation is, generally speaking, not that simple to compute. You can't just necessarily look at a data set and be able to eyeball what the standard deviation is. But this sort of tells you that, yes, we can quantify this value. We can actually quantify and assign a number to the amount of deviation, the amount of variation there is in a set. And that's measured by its standard deviation i.e. the average, with air quotes, average deviation from the mean. So I'm going to compute a standard deviation right now, and I'm going to take 5 randomly chosen values of SAT scores from a 2010 freshman class at Georgia Southern University. So there are 2,417 students, and I'm taking a random sample here of 5 of them. And what I'm going to do is compute the standard deviation of this set. So the first thing that you're going to do, if you want to compute the average deviation from the mean, well, the first thing you need to do is compute the mean. And there it is. It's 548. You add all these up, you divide by 5, and you will get 548. Now what we're going to do is something that looks like this. So I'm going to look at how far each data point strays from the mean. So I'm going to subtract the mean from every data point. So 650 is one data point, right? We're looking at the first one here, 650. And comparing that to the mean, I subtract the mean from that 650, and we see that 650 is 102 above the mean. 490 is 58 below the mean. 580 is 32 above the mean. 450 is 98 below the mean. 570 is 22 above the mean. So you would think that it would be a great idea. Look at these deviations from the mean. You just add them up and divide by the total number, right? And that'll give you the average deviation. Well, there's a problem with that. When you add up the deviations from the mean, you will always get 0. So, right? Will this always happen? Yes. Whenever you do this, this will always happen. So mathematicians have come up with a way of dealing with this problem. And the way they do it is by squaring every value. So in other words, all of these deviations, you square them. So we square 102, and we get this number, 10,404. We square this deviation, negative 58, and we get 3,364. And we do that for all the deviations. And what we add up is not the deviations themselves, we add up the squared deviations. So here it is. Here's the sum of the squared deviations. In other words, if I add this number plus this number plus this number plus this number plus this number, we will get this number, this highlighted number. And that is the sum of the squared deviations. All right. So once you're there, I mean, we're just a few steps away. You divide the squared deviations by 1 less than the number of data points. Now, that might seem a little bit weird, but there is a reason. There's a very technical reason for why we do that. And I'm not going to go into the specifics of it, but it makes it better at estimating the overall population standard deviation. But that's all I'm going to say about that. So we divide by 1 less than our sample size, which was 5. So we divide by 4. So sum of the squared deviations, divide by n minus 1, and we get this value here, 6,220. And when we take the square root of that, yes, and by the way, I should say that when you do that, you get a number called the variance. So in other words, when you divide the sum of the squared deviations when you divide that by the number of data points minus 1, you get the variance. And when you take the square root of the variance, you have the standard deviation. So taking that square root almost in some sense undoes taking all of these squares. So, right, squares and square roots sort of undo one another in some sense. And in this way, to bring it back down to to the same sort of level, if you will, we take a square root, and this number represents a measure of the amount of variation there is within this data set. So the typical deviation from this mean of 548, the most typical, is 78.87. That's how we think of the standard deviation. So the variance is the average, in air quotes, of the squared deviations, and the standard deviation is the square root of the variance. The most common measure that you are going to see for measuring the variation in a set of values is the standard deviation. Okay, so generally speaking, this is how we do it. You compute the mean, you compute the deviations from the mean, you square all of those deviations, you add them up, you divide the result by the number of data points minus 1, and you take a square root of that, and you will get the standard deviation. So this is a verbal description of that process. Here is a mathematical description of that process, and whichever one you prefer to use, you're more than welcome to do. But again, if you read this, if you just pick this apart, it's really not as bad as it looks. I know, yes, I know, it looks terrible. Don't get me wrong. But you can look at this and say, okay, if you look at this upper part here, what a formula does is it gives you all of those steps in a very compact notation. This under the square root here, this upper part, the numerator, tells us that we add up the sum of the squares of the deviations from the mean. And then we divide by 1 less than the sample size, and we take a square root. Boom, there it is. So this formula, without having to write all of this stuff down, this is not, I'm not saying a verbal description is a bad way of doing it, but this mathematical notation here is a very succinct and compact way of writing that formula. Of writing that recipe for computation. Okay, so there it is. And typically standard deviation, particularly from a sample, is denoted as S. So a sample standard deviation is given by that formula. So one thing I would like to remind you of, and this is something that I will encourage you at this point to start doing, is learning how to use technology to do these things. Because I'm not going to expect you to do this by hand. In other words, I will not expect you to make a table like this. What I will expect you to know is how to interpret this number and what this number means. You should know that. But you should also know how to use technology. So if you want, I have here a, I guess that's not, it's not, I need to fix that link. So let's hold on here for a second. All right, and we're back. So I fixed that link, and hey, look at that. So there is a little manual here that will tell you how to use your TI-84 for calculating these things. So the first thing you need to do is learn how to enter a list, and so you can put that in there. And you can also find the standard deviation as well. So yeah, there it is. Find the sample variance or sample standard deviation, and it will tell you how to do that. Now, if you want, you may use that manual as a reference. I will tell you that there are a lot of great videos on YouTube that will show you how to do that. Now, if you don't have a TI-84 calculator, but you have something like the TI-32 or the TI-34 multi-view or whatever else you have, there are videos for that as well. So whatever calculator you have, it should be able, for the most part, to you should be able to calculate standard deviation with that. So you need to know how to enter data into your calculator and how to calculate a standard deviation. On the other hand, if you're feeling a little bit lazy, you can always use the website. So you can see there's a link here for the Holt.Blue statistical software suite. And one thing I will also give you here, let me show you how that actually works. You can go to that statistical software suite by just going to the main page and hitting Statistical Software Suite. And hey, look at that. When you go to this one variable descriptive statistics calculator, it'll take you to a window. You put your data into this window, and since it gives you a histogram, you also need to give it a bin width as well. So if we paste the, what is this? This is the North Carolina commute time data into the, we're putting this into the calculator here. We're going to do a width of 10, right? So a bin width, the width of those bins in our histogram is going to be 10. And when we calculate it, hey, look at that. It gives us that distribution. So if we go back to that stem and leaf plot, right, you can see that that stem and leaf plot looks a lot like this histogram. That's because it is, because the bin width is 10. But also, look at this really handy thing. Hey, it gives you the standard deviation. So even though there were 15 points, we don't have to compute, all, the mean and then all 15 deviations from the mean and then square them, add them up, divide by n minus 1, take a square root. We don't have to do any of that. Software will do that for you. And typically, one thing I will tell you is that whenever statisticians or mathematicians or anyone else are doing statistics, they don't do it by hand. They use technology. And I'm hoping that you will do the same thing. Don't do this by hand. Use your calculator, use Holt.Blue, use some kind of software package that will enable you to do that. So there you have it, but you should know what that means. In other words, that 15 tells us that the typical deviation from this mean of 22.46 is going to be about 15. In other words, that typically a deviation from the mean is within 15, right? But of course, we've seen, right, there might be outliers. Who really knows? But sort of the typical deviation from the mean is about 15. And it tells us sort of how widely distributed, how spread out our distribution is. That's really what this number gives us. And it quantifies how spread out our distribution is. So yeah, so another way of thinking about this too is the skinnier the distribution, the smaller this number will be. The more spread out and wide the distribution is, the bigger this number will be, the bigger the standard deviation will be. Okay, so one more generic piece of wisdom here for you, and that'll be the end of it. So a really common summary for a distribution is the mean and standard deviation. So I'm going to warn you that this is only a good idea if you have a distribution which is approximately symmetric. If you don't have a symmetric distribution or anything that looks close, if it's a skewed distribution, then the mean and the standard deviation are not a good way to summarize the data. The better way to go would be using this thing. Do you remember what it's called? Yes, it's called the 5-number summary. So use the 5-number summary if you see any skew or anything in your data set. Okay, so yes, that was a long lecture, but we've earned our keep today. So we will see you next time.